Tushar, am I audible? Okay. Yeah, so welcome everyone. So I'll wait for 2-3 minutes and then I'll start the class. Yeah, so before I start, what is the progress of the course? I mean, have you all gone through the week 3 lectures? Can I get an update?
Yes, sir, we are going through it.
Okay, so um, in week 3 we have strain, and in week 3 we have concepts of strain. So, and in the coming weeks I can see we have the concept of stress. So both of the lectures are floated, right? Week 3 and week 4 are available to you, right? Hello.
Sir, a little bit more clear.
I was asking if week 3 and 4 are available to you or not.
Lecture notes.
No, the lectures in the, like,
Yes, sir, it's
professor,
available.
it's available.
Sir,
So
it's available.
okay, week 3 is available. It's showing the week 4 is also available. So what is the progress? I mean, have you gone through it, or like what is the progress? See, you can be frank. Okay, not yet. Okay. Um, no, sir. Okay. So then I have just recently joined the course. Okay.
Sir,
Yeah.
since I'm not from the background of geology, it's a little bit difficult to grasp the concepts correctly.
Okay. So in the previous class, we had a class on stereo net. Was it clear? Was it good?
Yes,
Or
sir, it was clear. Yes, sir, it was good.
okay. So what do you mean by the concepts are not clear about strain? You mean?
Sir, I didn't note those concepts which I was not understanding.
About strain?
So wait, sir, I have some network.
Okay, no, no, don't worry. You can write it on the chat also. In the chat box, you can write. Okay, so anyone else? Sir, are these problem solving classes recorded? Yes, these are all recorded. So in structural geology ce98 course, we don't have that much of difficult problems. So I decided, to run it more like a tutorial where I will, clear your doubts and, teach a little bit theories so that it will help you to grasp the subject. All right. So we have students from different backgrounds here, I think, and so to cater the demand of the vast, okay, yeah, yeah. So cater the demand. So I have to be a little bit, fundamental. So I'll I'll try to. clear the concepts in these classes. So these are recorded, so you can see it in the structural geology portal. Yeah, so there is a tab. Let me share my screen. Can you give us more example problems with solutions? Yes, we actually we can, but the thing is that we have some boundaries. Like there is a these problems will be accessible if you register for the course. So the registration is there. The registration is open. So if you register for the course, be you will be having the access of the problems. So have you registered for the course?
Yes, sir, I have registered.
No, yeah. So I was talking to the person who just said these things in the chat. His name is Aisha Rafiki. Her name, yeah, Aisha Rafiki. No, Ram. Okay, yeah. Okay, so yeah. Okay, all right. Yeah. So you want more problems? Then is there a payment for registration? Yes, there is a very nominal payment. So it's if you register before 12th September, it will be 1,000 rupees, I think. And after 12 to 16 September, it will be 1.5k. So, but you will get a certificate that you completed this course and you will be evaluated. So there is that. And 1,000 rupees, I don't know. I mean, there are like other platforms, teaching online teaching platforms, which okay, yeah. So which compared to which this NPTEL is little bit cheap, and you are getting professors from IIT Kanpur. So yeah, so there's that. Yeah, so let's start today's class. So to answer your question, can you see the tab here, problem solving session?
Yes, sir.
Yeah, so if you click here, you will see that there will be some kind of links. Yeah, if you click this link, some another tab will open, and here you will see the recorded lectures of this class will be recorded and it will be uploaded on YouTube. So you can see the previous classes, and today's class will be somewhere here in the week 3 tab. Yeah, all right. So today we'll be starting with strain. Is it okay, or do you have any doubt about stereo net of the previous class? Otherwise, I will jump straight into the strain. Does anybody have any doubt?
No, sir.
Okay, I guess. Okay, yeah. So when you learn the kinematic part of a structural geology, so the first thing that you encounter is deformation. So structural geology mostly deals with deformation, and you have to quantify it, right? So what is meant by deformation? Um, so for example, uh, a rock, if it undergoes some pressure or temperature, it will feel some kind of force, right? And it will change its shape, and it may rotate, or it may get translated to another part of the bed. So these things happen, like in when the rock is deforming, it changes its shape. The volume may get increased, the volume may get decreased. So these things happen, right? So all of these things, it comes under deformation. So for example, here is a video from YouTube. This is showing a flock of birds, right? You can see the flock is deforming, right? It's changing its shape. But if you look closely, if you point, if you are standing somewhere here, you will be able to. Can you see the pointer? I don't know. If you cannot see the pointer, just tell me. Huh? Can you see the pointer?
Yes, sir.
Yeah, so if you are here, standing here, you will see that the shape of the flock is changing, right? So with time, the flock is, you can say, it's deforming. But if you look closely, like the distance from one bird to the another, it's not changing that much, right? So when you are measuring the deformation, the scale is very important. So from where you are, measuring this kind of displacements or this kind of motions, all right? So when you are measuring, suppose you are measuring a deformation of a particular rock, and that particular rock has some kind of fossil in it, all right, and it is broken like that. So this is the fossilized part, and it's broken like that. So initially the fossil was something like that. Okay, so now when the rock got deformed, it got extended, and the part of the fossil being brittle, it got separated. All right. So if you are measuring the strain from outside the a reference point outside the fossil, you can measure the strain. But if you are inside the fossil somewhere, if you are measuring the strain here, maybe you won't see any strain, right? You have to consider the whole body, right? Am I clear? Sorry.
Sir, can you please repeat?
For example, reference frame is the primary thing that you have to set for any kind of measurement, right? You have to set from where you will be measuring the strain or the deformation. All right. So when suppose any body like that, any body, don't confuse, like it may be a fossil, maybe something else. If you have a longitudinal body like that, so with time, if you extend this, what will happen? It will break, right?
Yes, sir.
So if your observation contains the whole thing, if you're observing from a reference point outside this body, you can only then measure the strain. Otherwise you cannot measure the strain. If you are somewhere here, when you break the body, you will see that the other parts are very close, like the birds. Got it? So if you observe from a point outside this body, then only you can measure you can see that there is some kind of displacement, right? Is it clear?
Yes, sir.
Yes, sir.
Okay. So suppose you have uh, a motion, right? A particle, you is the suppose this is your mineral grains, and at later instant of time you get a deformed rock where the mineral grains have changed their positions, right? So if this is the initial position I, and if this is the final position F for a particular mineral grain, and the mineral grain might have uh, traveled through this path with time, but when you are seeing only the final position, and suppose you have a record somewhere of the initial position, or you can reduce the initial position, this will be the velocity path, this won't be the particle path. So the velocity path is basically the displacement of the point at two different time instants, and particle path will be the history of how the particle has traveled. Is this clear?
Yes, sir.
So why this is important? This is important because when we study the rock, we only see a final picture. We do not know what happened in between. So mostly we will have to work with the velocity paths, right? So suppose you are watching, like everybody here watches cricket, right? So if you see a ball that has been outswing or outswing something like that, if this is the wicket, you will see this is the particle path where you will see the every instant of the ball is recorded. But if you consider only the velocity path, the motion will be something like that. Suppose this is where the ball is left, and this is up to where the position of the ball is measured. All right. So the difference of particle path and velocity path is clear. Hello.
Yes, sir.
Okay. Yeah. So deformation has all of these things. Let's say, for example, you are seeing a garnet in a thin section. Have you seen a snowball garnet in thin sections? Are you familiar with the term snowball garnet?
Yes, sir.
Okay. So yes, if you see a snowball garnet, you will see somewhat like that. Okay. This is the garnet. This is the garnet. So garnet appears to be rigid with respect to the uh, the cyst, maybe in which the garnet is situated. So the garnet will be rotated at some time of at some point, and this rotation, or maybe there might be some kind of translation. So all of these things, say for example, if you see a cystosity, something like that, right? This will be considered as distortion. So all of these things come under the deformation, right? But if there is a volume change and a shape change, then we will consider that that particular region of the rock is strained. Is it clear?
Yes, sir.
Okay. So, say for example, initially an object at time instant t0 had a volume like this one, and with the time instant t1 or tf, it has a volume of this much. So the volume change del v, that is vf minus vi, will it be positive or negative?
Positive.
Yes, this will be positive because vf is definitely bigger than vi. But if you have an instance where this is the initial volume and this is the final volume, what will be the volume change? Del V is will be positive or negative?
Negative.
Yes. So if the pressure increases, if the force increases, say for example, a particular part of a rock is going down in a subduction zone, so it will encounter more and more pressure when it goes down, right? So everything, so as the lithostatic pressure will increase, so the volume strain will increase, and your del V will be negative, right? All right. And if a rock is exhumed, if it's coming upward and it is experiencing less and less lithostatic pressure, so it will expand its volume, so the volume change will be positive. All right. Now For the shape changes, say for example, if you have a body or a grain somewhat like this, right? And with time, it got distorted and became somewhat like this, right? So there is a change of shape. So the strain also affected this grain, right? If a object is like that, like a regular rectangle, and a later instant of time, if it becomes something like that with the shear force, then there is also a shape change, but there is no volume change. Here we have both the volume change and the shape change, but here we have only the shape change. There is no volume change. So all these instances we can calculate the strains, right? But to do that, we have to be sure like what kind of strain has affected the body. Is it the deformation? Is it homogeneous deformation? Or is it the heterogeneous deformation? So for homogeneous deformation, the definition is very straightforward. Say for example, if you have a body where you can have two features which are parallel, then after the homogeneous deformation, these lines, whatever be the shape change or whatever be the volume change, whatever be it, it will be parallel, right? For heterogeneous deformation, it is also more or less straightforward, but what will happen is that in case of heterogeneous deformation, your parallel lines, initially parallel lines, won't be parallel. All right? Is this clear?
What do these parallel lines represent exactly?
Any, say for example, if you have a suppose if you have a fossil, right? These are some kind of internal features of that fossil. Okay. So for example, you are considering this line and this line. So after homogeneous deformation, suppose the fossil is looking somewhat like this, right? But these lines will be parallel. But if it is affected by heterogeneous deformation, then the shape will be somewhat like this, and the lines won't be parallel anymore. All right, it will be somewhat like that. If you go through the lecture, there is a beautiful photograph. Can you see the lecture? Can you see the slides?
Yes,
Yes,
sir.
sir.
Yeah. So, say for example, in this case, the homogeneous deformation took place. So if you have two lines somewhere here, it will be parallel. If you have two lines somewhere here, it will be parallel here and it will be parallel here also, right? But if you have heterogeneous deformation where you just squeeze the body, right, like this, okay, so you won't have any parallel lines. Say for example, here or here, you won't have any parallel lines which were initially parallel, right? Is
Okay,
it
sir.
clear?
Yes, sir.
Yeah. So can I move forward with the measuring techniques? Like how are we going to measure strains and all those things? Is this clear? I mean, if you have any question, you can ask straight away. Okay. Do you have any question?
Sir, So basically, volume and shape change is strain, causing strain, and translation and movement. That doesn't mean strain. Is it what you talked about it before?
Yeah, so if you are in a reference frame where you are seeing only translation, but I mean the whole body is translated. Suppose you are looking at a body here, and at later instant of time, you are at a reference frame where you are seeing the nothing has changed, right? So if you have a reference frame inside that body, so there will be zero translation also, right? But if you are outside somewhere here, you can see the body has moved from here to here, right? So that is also translation. So if you want to calculate like how it is affected the outer part of outer part of the body, then there will be strain, but the body is not affected by strain, right? So every part of the body is exactly same at the initial instant and the final instant. All right.
So
The,
is that strain?
no, that is not strain, but that is deformation.
Oh,
So
okay,
we
okay.
cannot tell that the body is strained, but we will tell that the body is deformed, right? Deformation, any kind of rigid body rotation, any kind of movement, any kind of change in displacement, any kind of change in relative position, all of these encompass the term deformation, right?
Okay,
But
sir.
if you want to measure the strain, you have to choose a particular reference point where you will see some kind of shape change or volume change. Then only you will say that that particular body is strained. Is this clear?
Yes, sir.
Okay. Uh, so to measure strain, we have to find the markers in the rocks, right? That marker can be fossil are excellent markers because they have a very low very low tensile strength relative to the other parts of the rocks. And so what happens is that suppose you have a fossil like that, longitudinal fossil like that. So what happens and it is within a rock, right? Within some kind of sedimentary rock. So if you extend the rock, you apply force in this two direction, the whole body will try to expand, right? And due to the competency contrast, what will happen? This will break to several pieces, all right? And we will see only this final image, right? We'll only see the fossil that is broken, right? So can we measure the strain from here? Hello, any idea? Say for example, the body has an initial length L0, and from the paleontologist we know, suppose this particular species has some kind of length else of a full grown organism has a particular kind of length L0, right? But we are seeing a total length of, say for example, uh, LF, right? So can we measure the strain from here? Hello, are we familiar with the concepts of longitudinal strain, Young's modulus, Are you familiar with these terms? Hello?
Yes, sir.
So we are familiar with those terms, right?
Yes, sir.
So any idea how will we measure the strain of this that has affected this portion of rock, or maybe only this belemnite fossil? It's very easy. So you have a final length, that is LF, and you have an initial length from the paleontological record. Okay? From the paleontological record, you have an initial length that this particular organism can be, say, for example, 5 centimeter long, not more than that, 4 to 5 centimeter. So we can consider this as 5 centimeter, right? L0. But now we are seeing that the L, will it be greater than 5 centimeter or less than 5 centimeter? What will be the length?
Greater.
Greater, yes. So say for example, this is 7 centimeter. Now we are measuring LF to be 7 centimeter, right? So what is the strain? Can we calculate from here? So the formula of strain is del L by L0. That is LF minus Li or L0 divided by L0, right? So this is strain, right? So what will be the strain here?
2/5.
Yes, so it will be 2 by 5. So del L will be 7 minus 5 by 5. So it will be 2 by 5. And what will be the unit of strain?
No unit, right?
Sorry?
Is no unit, right? There's no dimension.
Yes, so it will be dimensionless quantity. So whenever you measure strain, be it a linear strain, be it an angular strain, be it any kind of strain, the strain will be always unitless, right? It is a dimensionless quantity. It's a ratio, right? So we have covered how we will measure the linear strain. The another term, so longitudinal strain is basically, as I have written here, epsilon, that is equal to the ratio of length change by the initial length. But there is another term that we frequently use, that is stretch, right? So for computational convenience purpose, we use this term stretch, which is basically 1 plus epsilon, right? That is basically the ratio of final length to the initial length, right? So what will be the final length? The final length will be the change in length plus the initial length divided by, in the denominator we have L0. So that is basically 1 plus del L by L0, that is basically 1 plus epsilon, right? And that is equal to capital S. That is stretch. And there is one more parameter which is called quadratic elongation, lambda, which is basically square of S. That is 1 plus epsilon whole square. Alright. Why do we have to introduce this term? If in the next class, if you go through all the lectures about strength, it will be easier for me, to communicate. The next class I am planning to show you some mathematical derivations, so that in that you will see we will deal with the equations of ellipse and the equations of circles, right? So in that we will solve quadratic equations. So if you bring in the term lambda, then our equations will be easier to handle. That's why people have introduced this term quadratic elongation. And we don't have to worry about the sign also if we use the quadratic elongation. All right. So these are all about terms that are related to linear strength. There is another thing in structural geology that we use, that is called angular strain. As I said, that if the volume is changed, then you will only have to deal with this linear strain. Suppose, say for example, if you are measuring strain in 3 dimensions separately, you if you have the data of them, you can calculate the volume change, or you can measure the volume like independently, and you can calculate the volume strain. But if you have a shape change, that means that each part of this particular body have rotated. The angular relationship of this body, if it is deformed, like that, so the shape has changed, right? So the angular relationship will be different. So this angle theta will not be equal to this angle theta f, right? So theta 0 will not be equal to theta f. So there is some kind of angular strain parameter that we have to deal with. So for example, there is a body. Now it got deformed by some kind of simple shear force, right? And we want to measure the strain along this axis. All right. So what we have to do is we have to consider what is the angle that has been traversed by the perpendicular on this line, right? So it has traveled this much angular rotation. Are you all with me? So in the clockwise direction, it has traveled this much of an angle, right? Is there
Yes.
any? Yeah. So the angular strain is defined as tan of psi, that is equal to del x by y. Okay. So we are measuring the shear strain along this line. So it will be del x on the numerator by the axis perpendicular to the line of measurement. All right. And that is called shear strain. Okay. Am I clear?
So shear strain is the tan of angular strain.
Yes.
Okay, sir.
Actually, shear strain is the tan of angular displacement, right? So this psi is basically del of theta, you can say, right? So it's the angle. This is not strain, this is displacement. So whenever you whenever you say strain, it will be some kind of, always some kind of a ratio, right? So this is the angular displacement, and tan of this angular displacement is shear strain. All right.
So what is angular strain?
Angular strain is shear strain. Angular strain is the strain that we calculate not by the usual displacement. Say for example, if you have a body like that, and with time you are extending the body, right? So there will be elongation. So you will measure the you will measure the lengths, right? But if you rotate the body, suppose you have a body here, and if you rotate the body and the body changes position here, there will be angular displacement, right? So if you want to calculate the angular strain along this line, this is how you will calculate. You will calculate the angle psi. You will calculate the angle psi and you will take the tangent of psi. This is how you will calculate the angular strain or shear strain.
Okay, sir.
Is it clear now?
Yes, sir.
Okay. But there is a thing about angular strain, that is, if you measure the rotation in clockwise direction, then the strain will be negative. If you measure the rotation in a counterclockwise direction, then the strain will be positive. It's just a sign convention, right? So if you are telling that the body has an angular displacement of minus 30 degree, then everybody will understand that the body has rotated 30 degree in a clockwise direction. This is the initial position, this is the final position. This is what they will understand. And if you say that the body has an angular displacement of plus 30 degree, then they will understand that the body has rotated in a counterclockwise position. This is the initial position, this is the final position. All right?
Okay, sir.
I can only hear one voice. So others, are you getting what I am writing on this note, or is it I am not able to connect with you? What is happening? Hello?
Hello, sir.
Yeah. Hello?
Why?
I see. The thing is, changing length divided by original length. Okay. So the thing is, if you do not interact, then it will be. I won't know. Like if you are getting whatever I am writing on this note, or is this all right?
Yes, sir.
So now we have an idea like how a body can rotate or how a body can deform, these ideas that we have. So now what is happening, say for example, in the natural condition, you do not get any kind of particular say for example displacement or only rotation. You always see a mixture of little bit of both, right? So if you see that the body is rotating, say for example, and if you are seeing that the body is not rotating, so then two kinds of phenomena can happen actually. What is that? Suppose this is your initial body, all right? So with time you are deforming the body and it became an ellipse, all right? Now in another instant, that if this is the body and with time it became a slanted ellipse like that. So what is the difference between these two? If these are the two lines that are perpendicular inside the body, so in this case it will also be perpendicular like that. So there will be zero rotation of the principal axis. These are called principal axis, right? But in this case, it will be rotated and it will become something like that, right? So there is a rotation in this direction. So this line will be here and this line will be here. So there will be rotation, and we call this kind of deformation as coaxial deformation. And this kind of deformation where that involves rotation, we call it non-coaxial deformation. All right. So that, I think, sums up the week 3's first lecture. So there is another thing in, so whenever Tushar, can you please mute the sound? Yeah, thank you. So in case of coaxial deformation, we call this kind of deformations as pure shear. But in case of non-coaxial deformation, we call the shear deformation as simple shear. Okay. So I think this will help you understand, at least start with the lecture that sir has given. So if you have any more doubt regarding the lecture or any more doubt regarding today's class, you can ask. Okay. Hello, is everyone there?
Yes, sir.
Yes, sir.
So yeah, if you have any more doubt regarding this class or anything that I can help you with. So what is simple shear and pure shear?
Simple shear is when the rotation happens. It is also known as non-coaxial deformation, and pure shear is where there is no rotation.
Yes. So in simple shear, if this is the initial block, so there is no rotation, only force will act on this particular direction. So what will happen? It will become something like that. Okay? So there is no rotation involved, right? This is the final geometry of that block. That will be termed as pure shear. In case of simple shear, this is the same block. There will be shear force acting on it, and it will be something like that. Okay, it will be something like that. This is the final geometry of the block where the rotation will have take place. Okay, so there is one more thing that we um, use to to get an idea like what kind of deformation happened, that is called Flynn diagram. So are we okay with this terminology, epsilon 1 and epsilon 3? So in a deformation, there will be three axes: X, Y, and Z, right?
Yes, sir.
So X, the deformation on X, the strain on X will be coined as epsilon 1. On Y, it will be termed as epsilon 2. On Z, it will be termed as epsilon 3. So by definition, E1 will be highest, right? It will be highest than E2, and E2 will be, it will be higher than, larger than E2, and E2 will be larger than E3. Okay, so suppose you have an ellipsoid, right? So the largest axis will contain the E1, the direction of E1. The intermediate axis will contain the direction of E2, and the smallest axis will contain the direction of E3. Okay, or epsilon 3. Okay, so if you get all this data, then one, what is 1 plus epsilon 1? What is this term?
1 plus H1, 1.
Yeah, that is,
Stretch.
yes,
H.
stretch. Yeah, S1, right? And 1 plus epsilon 3 is S3.
Yes.
So yeah, so in a plot, this is a plot where you have, in the y-axis you have S3 or 1 plus epsilon 3, and in the x direction you have 1 plus epsilon 1. So you can plot the different instances, like suppose these are, these blue, light blue circles are the final positions, right? The dark blue is the initial position, right? Initial shape of the body. See, if you are, so what is this R1 line? This R equal to 1 line is the line where you have the, there is like E1 will be equal to E3. Okay, so there will only be some kind of volume change associated. There won't be any kind of deformation, right? So E1 and E3, this will be same. If there is a discrepancy with this strain, then it will become an ellipse. Am I clear?
Yes, sir.
Suppose you have a circle like that, and in this direction you have epsilon 1, and in this direction you have epsilon 3, right? If epsilon 3 is equal to epsilon 1, then you will only get a circle, maybe a smaller circle if these are negative, or maybe a larger circle if these are positive. Okay, but if you move in this field, you can see that the epsilon 1 and epsilon 3 both are greater than 0. So that means that the volume change will be positive, but there will be an ellipse. The final ellipse will be having epsilon 1 that is greater than the initial x direction. Okay, in this field where both are negative, there will be volume constriction, will reduce its volume, but by property epsilon 1 is greater. So this term will be, so it will have an ellipse in which the major axis of x will be bigger than the minor axis, right? Only in these two, only in these two directions where you will have like this one, the epsilon 1, epsilon 3 will be 0. So epsilon 3 will be equal to the initial diameter. Only you will get the stretch on x direction, right? But in this case, the x direction will be, same. Only the z direction you will get a shorten. This is how we read the Venn diagram where we can write that only field 1 we have stretching along x and y, and in field 2 we have stretching along x and shortening along y, shortening along. So this is a very self-explanatory diagram, but if you find any difficulty reading it, you can always ask. Okay. Okay. Is there anything else?
No doubt, sir.
Okay. So in the next lecture, you will find that lecture 6, you will find that the strain in 3D, how you can calculate the strain in 3 dimension. But for that, you have to go to the strain lecture part 1, where all of these things are explained, right? So there's some good diagrams. So this is a film diagram of 3D strain, where in the x-axis you will have one ratio, in the y-axis you will have another ratio, and this is how you will find different fields like constriction, flattening, right? So yeah, and there will be vorticity analysis, yeah, and that will be all about strain. So if you are interested to know more about strain, I can show you some mathematical derivations of how strain can be calculated in a matrix form, or how you can calculate strain and relate it with stress. So I will go towards that. Otherwise, I will explain like what are the different kinds of strains and how strains are calculated in this way. So it's up to you. So if you tell me now, it will be easier for me, to prepare. So what should we do in the next class? Hello? So you can write in the chat if you want. Go ahead with matrix for strain calculation. Okay. Anyone else for this? Will there be derivations for? No, there won't be. We'll see, these exams will be in multiple choice questions type, so in there you won't have to be derive some kind of formula or something like that. Okay. So what do? We go with the matrix.
Yes, sir.
Okay. So I got 2 votes on matrix. I have 6 to 7 more students in the class. So what do you think? Others, please opine. Okay. Okay. So we will meet in the next class. Yeah. Yeah. And wish you all happy Independence Day. So
Yes, sir.
we'll
Thank you.
yeah. So we'll meet in the next class. Okay. Okay. Okay, I'm ending the meeting.